Yeah, let's start with motion. So motion slash objects falling. And let's start with an example. So let's say that we're given the position of a rock thrown straight up from an initial height of 240 feet with an initial velocity of 32 feet per second is S of t equal to negative 16t squared plus 32t plus 240. We want to answer a couple questions. Typically, what is the maximum height the ball reaches? The rock, ball, rock, whatever. So I get, well, actually, sure. So how do we find the maximum height of the rock? Well, we have to find the moment when the rock reaches its maximum height. Typically in this framework, we're thinking of positive velocity as the ball or the rock moving upwards. Negative velocity is the ball, the rock. I should have said ball, moving downwards. We're kind of imagining that this rock has been thrown from some initial height off a building and taking some path like that. So we're trying to figure out when we get to right there and what the height is at that moment. So you can kind of see that before that moment over here, velocity is going to be positive. And over here, velocity is going to be negative. And we need this because we need velocity to have a direction. So we're going to find the velocity. Typically, the way we find the velocity as a function of time is by taking the derivative position. So velocity is the derivative position, which you can either write as ds dt, or more typically as s prime of t. And that's going to equal the derivative of this function here, which is negative 32t plus 32. I should mention a couple other small things. This position here is measured in feet, and time is measured in seconds. So the position is given by some number of feet, and the velocity, when we differentiate, and this is kind of an interesting thing I've noticed over the years, is that when you differentiate some sort of position thing or some sort of velocity thing, you kind of end up dividing by your units of time. So if you're given the position in feet and you take the derivative, you get the velocity measured in feet per second. Take the derivative of that, you get acceleration measured in feet per second, or feet per second squared. If you take the derivative of that, you get jerk. Like when you, like if you're driving, if you're accelerating, then you accelerate faster, you jerk forward. It's literally called jerk. That's feet per second, or feet per second cubed. We don't really talk about jerk, but it's kind of fun to say. So here, our velocity is given as negative 32t plus 32. And if we want to find where we max out, well, that's going to be where the velocity goes from being positive to being negative. So we're going to set the velocity, which is negative 32t plus 32, equal to 0. That's going to give us the time when we reach the maximum height. Solving this, I would probably just say 32 equals 32t, or t equals 1. This is a pretty common theme, that if you're trying to find where a function has a maximum or a minimum, you're going to take that function's derivative and set it equal to 0 to find the place where you have a maximum. Now, we're not done answering the question because we didn't ask what time is it when the ball reaches its maximum height or the rock reaches its maximum height. We asked, what is the maximum height? So we have to take that value that we found for the time and plug it back into the height function, the position function. So I substitute this one back in here. I can see that S of 1 is going to equal negative 16 times 1 squared plus 32 times 1 plus 240, which is going to be negative 16 plus 32 is 16 plus 240 is 256 feet. I probably should say this is time equal to 1 second. That's the highest height the ball reaches. The rock reaches. Just pretend like I'm saying rock if I say ball. What other fun things can we ask? How fast is the rock going when it hits the ground? Maybe we can move things around here. How fast does the rock hit the ground? Maybe that's not phrased very excellently. A better way of writing this question would be, when the rock hits the ground, what is its speed? Sometimes our intuition is a little weird here. Like you might kind of think, well, it's not going to be moving when it hits the ground, so its speed would be 0. But it's kind of like the moment as it hits the ground, we're saying, right? Because if your speed was 0 when you hit the ground, falling wouldn't be a problem. If I fell from, a tall building to the earth and I hit the ground with the speed of 0, I'd be okay. Obviously not the case. So let's figure out what's going on here. If I want to know what speed I have when I hit the ground, I need to find, again, the time when I hit the ground. So previously, to find the maximum height, we found where the velocity was equal to 0. To find when the ball hits the ground, we want to find when the height is equal to 0, or the position is equal to 0. So we're going to set S of t equal to the function it's equal to, negative 16t squared plus 32t plus 240. We're going to set that equal to 0. If you're doing this problem in the US measurement system, right, feet and seconds, and the person has designed the problem to turn out nicely, typically a 16 will factor out, or a negative 16. Not always. Lots of these problems don't turn out very nicely. This one will. We can factor out a negative 16 here, and we're left with positive t squared minus 2t, and 240 divided by negative 16 is negative 15. And then hopefully this factors. I'm looking for numbers that multiply to negative 15 and add up to negative 2. I think the numbers are negative 5 and positive 3. I think, right? Yeah, negative 2 and then negative 15. That works out. So at what times does the ball hit the ground? Well, time could either equal 5 seconds or time could equal negative 3 seconds. Negative 3 seconds doesn't really make sense here, right? Those would still, like, if you thought about the picture we had here, I mean, if you thought about going backwards in time 3 seconds would be where the ball hit the ground if you could go backwards in time and kind of follow the same path. But here, the right answer is just that the time that it hits the ground is going to be 5 seconds after we threw the rock. Again, we're not quite done because the question asked wasn't what time is it when the rock hits the ground. The question was, at what speed is the rock hitting the ground? And this is actually a question that has a little bit of subtlety to it. So let's go ahead and plug that time into the velocity equation and see what we get. So the velocity at 5 seconds is going to be, well, remind you, here's the velocity equation up here. V of t equals negative 32t plus 32. So plug in 5, I'm gonna get negative 32 times 5 plus 32. Multiply by 5. Let's just multiply by 10 and divide by 2. So negative 320 divided by 2 is negative 160. Plus 32 is negative 128 feet per second. And that is definitely the velocity with which the rock hits the ground. But that's not the speed. Because speed is always just a positive number. It's the magnitude of velocity. So our velocity at time equal to 5 seconds is negative 128 feet per second. Our speed at time equal to 5 seconds is the absolute value of the velocity at 5 seconds, which is the absolute value of negative 128 feet per second, which is 128 feet per second. You might hear people say this. You probably heard someone say this one. Velocity is a vector. It has to have a magnitude or a length or a size and a direction, either positive for up or negative for down in this framework. Whereas speed is just the magnitude. It's just how fast you're going. We don't care what direction you're going. Question? Okay. I thought there was something else I wanted to ask here. Maybe not. Oh, I know what it was. What's the acceleration of this thing? How do we find acceleration? Not quite. Yeah, so I take the derivative again. So here's my velocity equation. Acceleration is the first derivative of velocity or the second derivative of position. So if I take the first derivative of velocity here, the derivative of negative 32t plus 32 is going to be negative 32 plus 0. And that's going to be not feet per second, but feet per second, which we usually would just say feet per second squared. And what that really means is that every second, the velocity is decreasing by 32 feet per second. So if you drop the rock from the highest height, after 1 second, it'd be going negative 32 feet per second. After another second, it'd be going negative 64 feet per second. After another second, it'd be traveling at negative 96 feet per second. So it's speeding up, or its velocity is more and more negative the further it drops. Yeah, we're ignoring physics and air resistance and terminal velocity and all that stuff. We're just pretending like it speeds up as long as you want it to. But that's what acceleration is here. It's how fast the velocity is either increasing or decreasing. So other people might have framed this question differently and say, in fact, we can, yeah, let's talk about kind of working backwards for a second. Let's say that we are given, so here's a new question. We'll frame it in the metric system as opposed to the, what do you call the other? I don't even know, the US system, the imperial system. I forget what the name is. The not metric system, the harder to work with system. So given in the metric system that acceleration due to velocity is equal to negative 9.8 meters per second squared. If we throw, let's say a ball this time, ball upward with an initial velocity of, and let's just make the numbers terrible today, of positive 20 meters per second from an initial height of 15 meters off the ground. Find the position of the ball at time t. I'm writing this question in what I think is kind of the most terrible way possible to point something out. Questions are often written this way. They say, find the position of the ball at time t. What we really mean by this is write the position as a function of time. I don't know why people don't spell this out. seems super annoying when people write it this way, but you'll see this often. They're like, yeah, find the position at any time t or at time t. What they really mean is, oh yeah, right. It's kind of like with exponential growth and decay. When they say find the number of bacteria at time t, what they mean is write the bacteria, but write the function as a function of time. So that's what we're going to do. And we're going to start off with the fact that acceleration is equal to the constant negative 9.8. And we know that acceleration is equal to the derivative of velocity. We're kind of getting a jump start here on 21B. Yeah, we're going to think, I mean, we might not actually say the word antiderivative, but we're going to think about, oh yeah, how do you undo a derivative? Well, if I want my function to have a derivative that's negative 9.8, I need my function itself to be equal to negative 9.8 times t plus some constant. But then we know, or we have a way of finding the constant because we have an initial value. We know that the initial velocity, the velocity at time 0, or v naught, is equal to negative 9.8 times 0 plus my constant, but it should be equal to what we said the initial velocity was. Which almost feels like writing down too much. We're essentially just going to get here that our constant is equal to 20. So this equation becomes negative 9.8 t plus 20. It's got the right derivative. Its derivative is definitely negative 9.8. And it's got the right initial value. If I plug in 0, I get 20. And now we're going to do the same sort of thing to find the position function. People use S or H. I feel like I would probably more normally use H if I'm specifically talking about the height of something. But really, whatever letter you want to use, kind of fine. So we're going to do the same thing. Now we want a function whose derivative is negative 9.8 t plus 20. Well, I'm kind of reversing the power rule here, right? I know if I take the derivative of something, of some power, the power is 1 less. So to be able to undo that, I need my new power to be 1 more. So I need something like negative 9.8 times t squared. So it's not going to quite cut it. So take the derivative of that, I'm going to get negative 9.8 times 2t. And I want the derivative to be negative 9.8 times just t. So I better divide by 2 to account for that. Similarly, or not similarly, but continuing, the thing whose derivative is 20 is 20 times t. And then I also need a constant over here. I could also say c, but I'll use a different letter just for the sake of using a different letter. We kind of reuse c over and over again once you've dealt with it. And then we know that h of 0 is going to be 0 plus 0 plus d, and that should be equal to 15 meters. So d is equal to 15. So then our actual height function is going to be negative 9.8 divided by 2 is negative 4.9 t squared plus 20t plus 15. That's your height function. That's your position of the ball at time t, or your height as a function of time. And here's your velocity as a function of time, just because it's also meant to do that. These are pretty typical equations for objects falling through air or being thrown around in the air. Certainly, people can give other sorts of examples where they say you got a particle moving in space, and we're going to say its acceleration is something that's not just a constant, and then you can do kind of crazy things like that. But it's still the same idea, in that the derivative of position is velocity, and the derivative of velocity is acceleration. Yeah, I feel like that's enough of that, I think. We might come back to that. We might not. We got other things to talk about. So, speaking of repeated differentiation, there are some interesting functions that have some interesting derivatives. Specifically, I mean some trig functions. So if my function is f of x equal to, let's start with sine of x. The first derivative is cosine of x. But we know the derivative of cosine. The derivative of cosine is negative sine of x. So f double prime of x is equal to negative sine of x. And the third derivative, f triple prime of x, is equal to, so this is where we're going to use the constant multiple rule. If the derivative of sine is cosine, the derivative of -1 times sine is -1 times cosine. And I don't want to keep writing all these primes. It gets to be a little bit exhausting. So once you get past the third derivative, instead of writing all these primes, you start writing the fourth derivative as f with a superscript with a parentheses around a 4 to mean the fourth derivative. Without those parentheses, you don't mean the fourth derivative, you mean the fourth power of your function. So I just want to point out, if I wrote f to the fourth of x, that would mean sine of x to the fourth power, which you could write as sine to the fourth. So be careful. That parenthesis there is very necessary if to mean what you want to mean. The derivative of negative cosine is negative sine, which is sine of x. And sine and also cosine are kind of a unique couple of functions whose set of derivatives cycle. You can keep taking derivatives over and over and over again and just get back to the same thing you started with. So for example, if I said, oh, I should point out one more thing here. There is other notation. I could also say that this is equal to df dx. And this is, oh, sorry. Nope, that's the next line. Apologies. F of x is just the function. The derivative of f is the derivative of f. The second derivative of f double prime, can also be written as d squared f dx squared. And the rest of them follow the same sort of pattern. The third derivative is d cubed f dx cubed. The fourth derivative is d cubed. Sorry, oh my gosh, oh my goodness, oh my god, sorry. D to the fourth f dx to the fourth. They mean the same thing, just different notation. Sometimes this Leibniz notation on the right is more useful for whatever reason. Sometimes this notation on the left is more useful. One way this notation is more useful is in the following way. Let's say we want to find the 97th derivative of sine of x. Notice that I didn't write d at d97f dx97 because this sine of x is taking the place of f. I could, if you wanted to, write this more like this. Which feels less good to me, but it's still valid. So that is my, all right, that's my f. 97 derivatives, that seems like not very fun to do. We're not going to do all 97. Because the point is there that every time you do 4 derivatives, you get back to where you started. So what I really want to know is, what's 97 divided by 4? Actually, that's not what I really want to know. I really want to know what the remainder is. So 97 divided by 4, let's see. 2 times 4 is 8. Subtract. We're down to 7. 4 times 4 is 16. Subtract. One left over. So here's what I want you to see. This is equal to the derivative of the 96th derivative of sine of x. Right? This still means I'm going to do 97 derivatives. I'm going to do 96 of them first, and then I'm going to do one more after that. But if I do 96 derivatives of sine, I'm going to end up with sine. Because I'm doing 4 derivatives, 4 derivatives, 4 derivatives, 24 times. This means this is going to be equal to just the derivative of sine of x, which is then equal to cosine of x. In a similar-ish way, we could ask ourselves, oh yeah, we're going to make it more fun. We're going to ask ourselves, yeah, like more fun. Yeah, more fun. We're going to say, what's the, let's not get too crazy here. What's the 20, oh my gosh, can I write things? Let's just use a new page because I clearly cannot write the words I'm trying to say. What's the 23rd derivative of cosine of 2x? This is where things are going to get a little bit dicier. So before we start doing this, let's just think about what's going to happen here. Let's examine instead the 23rd derivative of just cosine of x. All right, let me ask everybody, show me on your fingers. If I divide 20 by 4, what's the remainder? See a few fingers. Yeah. Right, 20 divided by 4, 23 divided by 4. Did I say 20? Did I not say 23? Sorry, I'm blowing it. Sorry, if it did, you guys answered the question I was asking. Thank you. I meant to be asking. 23 divided by 4, the remainder is 3. So that means that when we do this derivative 23 times, well, the first 20 times are going to get us back to cosine. So you could rewrite this as going to be equal to the third derivative of, I guess I'll show all my work here, the 20th derivative of cosine of x. But the 20th derivative of cosine is just cosine. And then the third derivative of cosine is, let's see, derivative of cosine is negative sine, then negative cosine, then positive sine. Cool. So we know that when we take the derivative of cosine of x 23 times, we end up with sine of x. The difference here, in fact, let's talk about the difference here. Whoops, geez, wow, I'm really good at drawing today. The derivative of cosine of 2x isn't just negative sine of 2x. It's going to be negative sine of 2x times the derivative of 2x, which is 2. Chain rule. The derivative of cosine of some stuff is negative sine of the stuff times the derivative of the stuff. And then if I take the next derivative of that, this is where I would change notation, right? This is where I'm like, oh, I don't love my notation here. So what I would do instead at this moment is say, okay, I'm going to say that f of x is equal to cosine of 2x. And then my first derivative, f prime, is negative sine of 2x times 2. And then my second derivative is going to be the derivative of that, which is going to be negative cosine of 2x times 2 times another 2. Because I have to use the chain rule again. And then my third derivative is going to be derivative of negative cosine is positive sine of 2x times 2 times 2 times another 2. And we can start to see the pattern here, that every time we take another derivative, we get another multiple of 2. In fact, if we were being slick about this, we would say that this was negative cosine of 2x times 2 squared. And this was positive sine of 2x times 2 cubed. And so that whatever nth derivative we're taking here, we end up getting some trig function of 2x times 2 to the nth power. So if we go down to, say, taking the 23rd derivative of x of our function, not of x, the 23rd derivative of sine of 2x, sorry, of cosine of 2x. Well, we know that the derivative of cosine, the 23rd derivative of cosine is sine. So the 23rd derivative of cosine of 2x should be sine of 2x, but then we're going to end up multiplying by 2 to the 23rd power. Because every time we took a derivative, we multiplied by another factor of 2. Kind of a neat problem. There's not a lot of other functions that have cyclical derivatives like this. There's really only like 3 other ones, which we'll talk about eventually. Questions about anything that I did here? Let's talk more about the chain rule, because I feel like we haven't talked a whole lot about the chain rule, and it's kind of a big deal. So, yeah, we got that. So I think at this point we've learned how to take the derivative of most functions with maybe 1 or 2 exceptions. So a quick refresh, because I really want you all to see this. So, excuse me. We know that the derivative of x to a power is that power times x to the power minus 1. Good old power rule. I'm not gonna write down the product rule and the quotient rule here. We're just gonna take those. I'm talking about how to take derivatives of different types of functions. So we also know the derivatives of the trig functions. So we have the derivative sine of x is equal to cosine of x. The derivative of cosine of x is equal to negative sine of x. The derivative of tangent of x is equal to secant squared of x. And normally I would write these all next to each other, but I want to save room on the right side of this page here because I want to write some other things. So I'm going to write them kind of below. So now for the reciprocal functions, the reciprocal sign is cosecant. The derivative of cosecant of x is negative cosecant of x times cotangent of x. The derivative of secant of x, secant is the reciprocal of cosine, is secant of x times tangent of x. And the derivative of cotangent of x is negative cosecant squared of x. Quick reminder, all the co-functions, cosine, cosecant, cotangent, have negative derivatives. All the other ones, sine, tangent, and secant, have positive derivatives. And then I think the only other thing on our list currently is the derivative of e to the x is e to the x. I don't think anyone's quite gotten to the derivative of the natural log of x yet. But we're almost there. Okay, so these are what I kind of refer to in my mind as like the basic level derivatives, right? Here, straightforward derivative formula. And then every derivative formula that we know has a chain rule version, which really is the version you should actually think of. So instead of saying to yourself, the derivative of x to a power is that power times x to the p minus 1, I would instead prefer you to say the derivative of some stuff to a power is equal to that power times the stuff to the power minus 1. But then because of the chain rule, we have to multiply by the derivative of the stuff. Now, sorry, you can't quite see all that. Sorry about that. Most textbooks, instead of writing the word stuff, I should say all textbooks, instead of writing the word stuff, instead typically choose to use the letter u. So we often imagine that u is a function of x. So u is some function of x. And then we say the derivative of u to the p is equal to p times u to the p minus 1 times the derivative of u, which you might write as du dx, you might write as u prime. But the idea is still the same. And I really can't say this strongly enough. I would encourage all of you to say the word stuff inside of your head when you're doing these. Oh, I've got some stuff to a power. The derivative is the power times the stuff to the power minus 1. And then you'll have done this so many times eventually that you'll say, oh, I said the word stuff. I have to multiply by the derivative of the stuff. It'll be automatic. If you have some stuff to a power and taking the derivative, at the end of the day, you have to multiply by the derivative of that stuff. And the same thing is true for all of these formulas. So even though it's kind of tedious, you might not want to actually write all this down. You certainly never have to write anything down as far as I'm concerned. I mean, that doesn't mean you shouldn't ever write anything down, but like nothing's required. The derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. The derivative of cosine of some stuff is negative sine of that stuff. I need like a stamp with the word stuff on it. That'd be great. I'm not gonna ask for it. And the stuff prime. I need 2 stamps. I need a stuff and a stuff prime stamp. That'd be awesome. Anyway, derivative cosine of some stuff is negative sine of stuff times the derivative of the stuff. The derivative of tangent of some stuff is secant squared of the stuff times the derivative of the stuff. The derivative of cosecant of some stuff. Cosecant and secant are kind of weird. The derivative of cosecant of x is negative cosecant of x times cotangent of x. The derivative of cosecant of some stuff is negative cosecant of the stuff times cotangent of the stuff. And then we multiply by the derivative of the stuff. Don't worry, we're going to do some examples in just a second. Derivative of secant of some stuff does the same thing. is going to be secant of the stuff times tangent of the stuff times the derivative of the stuff. Maybe the most important word in all of calculus is the word of. When you're saying tangent, secant, cosine, whatever, I really, really, really would encourage you to say cosine of x, tangent of x, secant of, whatever you're taking secant. That of part there really kind of activates the fact that it is a function. You were doing this function and you're evaluating that function at whatever the argument is. Last couple ones here. Derivative of cotangent of some stuff is negative cosecant squared of that stuff times the derivative of that stuff. And finally, the derivative of e to the x is e to the x. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. Or you could use use if you like use. I like to say stuff. Okay, so we can use this for all sorts of things. For example, I could say, what about the derivative of cotangent of e to the x plus sine of x? So, all right, well, it's the derivative of cotangent of some stuff. And the derivative of cotangent of x is negative cosecant squared of x. So the derivative of cotangent of some stuff is going to be negative cosecant squared of that stuff. But then we have to multiply by the derivative of the inside stuff. Derivative of e to the x is e to the x. Derivative of sine of x is cosine of x. Or I might ask you all to try something like find the derivative of, sure, cosine of x plus tangent of x raised to the 7th power. Go ahead, give that a whirl. When doing problems like this that require the chain rule, the hard part can be identifying what I like to refer to as your outermost function. Like, what's the thing you're differentiating first? Here, I would read this as I have some stuff to the 7th power. So I'm going to differentiate like I have x to the 7th. The derivative of x to the 7th is 7x to the 6th. The derivative of some stuff to the 7th is 7 times my stuff to the 6th. But then I said the magic word stuff, I have to multiply by the derivative of the stuff. The derivative of cosine is negative sine of x. The derivative of tangent of x is secant squared of x. And we're not limited to just one iteration of the chain rule. Someone could ask us to say, take the derivative of, cotangent to the 4th power of x cubed minus x to the 5th. This way of writing this is usually preferable. Usually I would rather write this than the longer way of writing it. But here it's actually kind of detrimental to us because writing it this way makes it less obvious what our outermost function is. I would definitely choose to rewrite this as the derivative of cotangent of x cubed minus x to the 5th, all raised to the 4th power. And now it's, at least to me, it's more obvious that, oh, we've got some stuff raised to the 4th power. So when I take the derivative here, the derivative of some stuff to the 4th is going to be 4 times my stuff to the third power times the derivative of my stuff, which I'm actually going to write as the derivative of just the thing. So my cotangent of x cubed minus x to the fifth prime. And the reason I'm doing that is because I'm going to have to use the chain rule again. Because now if I want to take the derivative of that stuff, of the cotangent of x cubed minus x to the fifth, well, I've got cotangent of some new stuff. And I know the derivative cotangent of x is negative cosecant squared of x. The derivative cotangent of some new stuff is going to be negative cosecant squared of the new stuff times the derivative of the new stuff. So we're going to get 4 times cotangent of x cubed minus x to the fifth cubed times the derivative of cotangent of some stuff is negative cosecant squared of that stuff. And then I'm going to multiply by the derivative of the insides here, which I can do directly. The derivative of x cubed minus x to the fifth is 3x squared minus 5x to the fourth. Even though we could do some minimal simplification here, I don't see the value. If you have, if this is your answer on an exam, no one's asking you to simplify this. You should leave it as is. If you really felt compelled to, you might put this negative sign out in front. You might rewrite this as cotangent cubed instead of cotangent of this cube, but just leave it. And then we can get kind of very dramatic with all the things we can do, because we can start incorporating the product rule, the quotient rule, the chain rule, all these rules into one gigantic, terrible problem if we wanted to. Do I have enough room here? Yeah, sure. For example, I could say, so I'm going to change it up a little bit, right? I am a fan of this notation, d dx of my function, to write the derivative, because it's kind of the most compact way of writing it. But that doesn't mean it's the only way, right? I could say my function f of x is, let's make it terrible, x squared plus sine of x over e to the x times cosine of x, all raised to the 9th power. And I want to find the derivative, f prime of x. Or if you prefer, df dx. Great. So we're going to find the derivative. So we're going to have to end up using the chain rule and the quotient rule and the product rule. And the order is determined by kind of how we read, I'm using bad words there. The order is not determined by how we read it. No matter how we read it, the order is still set. We just have to be careful in our reading. So I am at the very kind of outer level seeing I have some stuff raised to the 9th power. So my derivative is going to be 9 times that stuff to the 8th power. Long pause, times the derivative of the inside stuff. Okay, to take the derivative of the inside stuff, I have to use the quotient rule, right? The derivative of x squared plus sine x over e to the x times cosine is requiring the quotient rule. So it's going to be the bottom times the derivative of the top. The derivative of the top is 2x plus cosine x minus the top, x squared plus sine of x, times the derivative of the bottom. Oh, that's where I'm going to have to use the product rule. The derivative of e to the x times cosine x requires the product rule. So for e to the x times cosine x, the derivative of e to the x is e to the x. Leave cosine alone. Plus, now we switch it up. You leave e to the x alone, and the derivative of cosine is negative sine of x. If I'd been a little bit more looking forward, I would have not written the plus sign there. I would have saved it and written the minus e to the x times sine of x, but I did myself in by writing the plus sign, so I was stuck. And then divided by the denominator squared. Gross. But not that gross. Maybe a little, not an unreasonable test question, I'm gonna argue. It's not lovely, but it's really not that terrible in the grand scheme of things. It's not asking you to be, I mean, yeah, it's kind of awful. I'm not gonna lie. It's not like, would I ask this on a test? No. But is it that bad? No. I can make one much worse. It's not a threat. It's just a true statement. All right, let's see here. We could do more of this, but really we should do some of that. Yeah. So all of this kind of chain rule business is not going away. The chain rule is going to live with you forever for the rest of your entire calculus career. Get used to it. All these derivative rules are never going away. You will need them in 21A, B, C, and D. I promise you. So get good at them now. Get good at the trig derivatives now. I've encouraged students for years to do this. Write down the 6 trig derivatives in the order I usually write them in, which is sine, cosine, tangent, cosecant, secant, cotangent, and their derivatives. Take a picture, make it your screensaver on your phone. Screensaver, what's the oh my God, words. What's that? Yeah, thank you. The wallpaper or your lock screen. That's what I did that, not with that, but with another thing. When I was teaching a math class a few years ago, and I had to learn some stuff that wasn't really sticking in my head because there was a lot of things that were equivalent to each other. I did that. I took a picture of it, made it my lock screen, and then every time I looked at my phone, I was like, oh yeah, this means that and that and that and that. And eventually I memorized it. So you definitely want to memorize these trig derivatives. You want to memorize all the derivative rules. They're not going away. So if you're planning on taking the rest of the math series, which I imagine all of you are, or at least some classes, you really need to know these by heart in your soul. Love them. Right? Tomorrow's Valentine's Day. Your Valentine should be calculus. In addition to whatever other Valentine you might have. But spend some time loving calculus. If you spend some time loving it, it'll love you back. All right. So, but the reason I'm kind of talking about the chain rule specifically here is that it really actually is all we're doing when we talk about implicit differentiation. So sometimes people are going to give us crazy looking things. And I'm going to give you the standard kind of nice example because one is something I can graph. So here's an example that's probably in your textbook. Oh, should we start off there for? Yeah, we'll do 2. Okay. So we'll start off with a couple examples. So example 1. Let's say we're given this equation. X squared plus y squared equals, sure, 25, which you might have already seen. It's a good example. That's why everybody uses it. So here's an equation where y is not a function of x. Right? If we graph this, it's a circle, and certainly it fails the vertical line test. And I still would really like to know, well, what's the slope of the tangent line at the point maybe like 4, -3? I would really love to know what the slope is. And there's 2 ways we could do this. Let me show you the first way, which is the less good way. One way we could do this is by solving for y. By the way, that's not always an option. For lots of other things that are defined implicitly, you can't solve for y. Here we can, so we will. Y squared equals 25 minus x squared. And if we take the square root of both sides, y is going to equal plus or minus the square root of 25 minus x squared. If we're on the bottom half here, that's definitely where y is equal to the negative square root of 25 minus x squared. So we are looking at specifically y equal to the negative, and let's write it in a way where it's going to be easier to take the derivative. So instead of the square root of 25 minus x squared, let's write it as 25 minus x squared to the 1/2 power. So now we're going to take the derivative, y prime, or dy dx, or whatever notation you happen to like. Get used to people switching back and forth because they do. It's going to be negative 1/2 times my stuff to the negative 1/2 times the derivative of the inside stuff, which is negative 2x. And just to be super clear here, the negative there isn't because it's because of what's happening here. It's because of the negative that was already there. Right? I'm bringing the 1/2 down. The new power is 1/2 minus 1, chain rule. And then I would probably simplify this. Negative 2 times negative 1/2 is just 1. So I'd write this as x over 25 minus x squared to the positive 1/2 power. And then we can plug in our point. I'm going to plug in x equal to 4. And then we get y prime at 4 is going to be 4 over the square root of 25 minus 16. That's the square root of 9. So I'm going to get 4/3, which looks plausible. That slope looks like it could be positive 4/3. Couple things here. One, this was a lot more work than it's going to be doing it the other way. Two, we had to actually know which piece of the function to use because, right, if I just not paid attention, I might have accidentally used the top piece and gotten a negative slope instead. But let's talk about doing this a better way. So I want to point out, whenever we do implicit differentiation, we are always making the assumption that y is a function of x, even if it's not really. A better word would be to say y depends on x, but we like to say y is a function of x. So what I really want you to think of is y is some stuff. I'll say it again. Y is some stuff. So if we go back to our original expression, original equation, x squared plus y squared equals 25, we're just going to differentiate both sides. X is the variable that we're differentiating with respect to. What's the derivative of x squared? Still 2x. Okay, here's what I want you to say when we do this next part. What's the derivative of some stuff squared? Oh, there's some stuff squared is 2 times my stuff to the first power. You don't really know the first power, but then we have to multiply by the derivative of the stuff. The chain rule is fully in play here. Y is a function of x. Look, y actually is a function of x. And so, continuing here, we also have to take the derivative of the other side. Derivative of 25 is 0. And now we can solve for y prime. So subtract 2x from both sides. I have 2 times y prime equal to negative 2x. Divide both sides by 2y, and we get y prime equal to negative 2x divided by 2y. And I would simplify that and say that y prime is equal to negative x divided by y. Couple things here. Thing one, if I plug in the point I'm looking at, y prime evaluated at 4, negative 3 is going to give us negative 4 over negative 3, which is 4/3, just like it did over there. The second thing, which is interesting in this instance, is that if you actually plug back in what y would equal to, you would get that the derivative is exactly what we found over here. If I plugged in y equal to negative 25 minus x squared to the 1/2 power, I would get y prime equal to negative x over negative 25 minus x squared to the 1/2 power, and the negatives would cancel out. So it really does give you the same thing if you happen to be in a situation where you could have solved for y in the first place. We're never going to find ourselves in that situation, but it could happen. So the main takeaway with implicit differentiation is that y is a function of x. And so when you differentiate something with y in it, we always have to multiply by the derivative of the stuff, which is just y prime, or dy dx if you prefer that notation. Let's look at some more examples. Oh, let's look at the other classic example that I want to talk about. So the next example, which is in the textbook, is this lovely example. What is the example? Yeah. X cubed plus y cubed is equal to 6xy. And this is one of the few implicitly defined functions that I will be able to graph for you. But you know what's great? You all have Desmos. You can graph some of these things, and the graphs are wild. Like, they're kind of neat to look at, though. I would encourage you to graph a couple of them if you have the time on Desmos. They're just kind of fun to look at. But here, I will tell you all that this function, I know 2 points on it. I know the point 0, 0, because 0 plus 0 equals 6 times 0 times 0. And we also have the point 3, 3. Because 3 cubed is 27, plus 3 cubed is 27, 27 plus 27 is 54, and 6 times 3 times 3 is also 54. Here's what this thing looks like. I'll try my best to draw it here. Again, there is a good picture of this in the textbook. Ooh, wow, okay. That's all right. I think it's called the folium of Descartes. It's kind of neat looking. But maybe I would like to know, what is the derivative of this? So I want to find y prime, or dy dx. I'm going to do the same thing I did before. I'm going to differentiate. And this is always our first step. Differentiate both sides of the equation. with respect to x. As far as we're concerned, at this stage of the game, 21A, everything's a function of x. Or what I mean, or I guess you could use t or something, but like it's never x a function of y, it's always y a function of x. That will not always be true. In 21B and 21C, we start kind of playing with the nature of which thing's a function of which. And for now, y is always a function of x. So if you really wanted, watch this for a second. I'm going to write this instead. We could write that we have x cubed plus some function of x cubed equal to 6x times a function of x. I don't recommend doing this every time or really any time because it's more writing, but let's just take the derivative of both sides. We differentiate both sides. The derivative of x cubed is 3x squared. The derivative of a function of x cubed or some stuff cubed is going to be 3 times our stuff squared times the derivative of our stuff. Equal to, on the right-hand side, we're going to have to use the product rule. We have a function of x times a function of x. And I would keep this, I like to think of it as 6x times f of x. So the derivative of 6x is 6. Leave the other thing alone. Plus, and now we switch it up. Leave the 6x alone. And the derivative of f of x is the derivative of f of x. Okay, but here's how people would actually have written this. They wouldn't have done this whole f of x thing, and they would have said, we have 3x squared plus 3 times y squared times dy dx equal to 6 times y plus 6x times dy dx. Just replacing every f of x with y and every f prime of x with dy dx. So when I look back here at this original thing, I'm like, oh yeah, the derivative of x cubed is 3x squared. The derivative of y cubed is 3 times my y squared times the derivative of my inside stuff y equal to, okay, product rule here. Derivative of 6x is 6, leave the y alone, plus leave the 6x alone. Derivative of y is the derivative of y. The shortcut way of thinking about this is that every time you have something with a y in it, you always have to end up multiplying by dy dx or y prime. But the better way to think about it is that your y is a function of x. And whenever you differentiate something with it, you always are using the chain rule and multiplying by the derivative of your stuff. And then after this, it's an algebra exercise, which is not to say it's nothing, right? There's still work to be done here. If I want to find the derivative, I have to solve for dy dx. That typically means identifying all the terms that have dy dx and bringing them all to the same side of the equation and everything else to the other side of the equation. It doesn't really matter which side you pick. If given a choice, I try to make as many things positive as possible. Here, it's not going to really matter either way. I'm going to bring the dy dx to the left and say I have 3y squared times dy dx minus 6x times dy dx equal to 6y minus 3x squared. I would then factor out, and normally, actually, if you want, you can kind of do the factoring at the same time. Like we could have, as you brought this up, like, oh yeah, we're going to factor out a dy dx and have a 3y squared minus 6x still equal to the same stuff. And finally, dividing both sides by the stuff multiplying dy dx here, we're going to get the dy dx is equal to 6y minus 3x squared over 3y squared minus 6x. Normally, there's not a lot of factoring that can be done here, if any. Here, you can factor out a 3 from the top and the bottom and say that dy dx is equal to 2y minus x squared over y squared minus 2x. But normally, you're not looking for any factoring. And then we can answer a fun question. What's the slope of the tangent line at the point 3, 3? Actually, better question. What's the equation of the tangent line at the point 3, 3? The equation of the line tangent at 3, 3. Well, we've got the point. We need the slope. The slope is going to be dy dx. People usually, when they write this, they write it dy dx. Sorry, it's really small. I'm sorry. Dy dx evaluated at, with a vertical line like that, and then the point 3, 3 at the bottom of that vertical line. It's kind of weird notation, I think, but that's what people do. And that's going to be 2 times 3 minus 3 squared over 3 squared minus 2 times 3. That's going to be 6 minus 9 over 9 minus 6, which is going to be -1. So my equation would be y minus 3 equal to -1 times x minus 3, which ends up being y equal to -x plus 3 is plus 6. That would be the equation in my hands at that point. Oh, you can't see that, sorry. Sorry, way off here. Okay. How much time have I got here? 5 minutes. No, 15 minutes. We're at 2:30, right? Yeah, 2:30. Sometimes the 10-minute thing always throws me off here. You would think after being a student here for many years and also teaching for many years, it wouldn't, but it still does. Okay, let's look at a couple more things because there's a couple interesting nuances that I want you to be aware of. Yeah. So let's do the following. Let's say we want to find dy dx given, we're just going to make up something truly heinous here. X squared plus y cubed equal to, let's say, tangent of, yeah, x, y plus, no, it's fine, plus 5. Okay, this problem has maybe an extra additional amount of terribleness to it. Here's why. We're going to differentiate both sides. That's always the first step. How do I know I'm using implicit differentiation here? Because you've got all these x's and y's mixed up together, right? You can't solve for y. If someone says differentiate this and they don't tell you use implicit, they still need use implicit because there's no other way to approach it. So if you see a bunch of x's and y's jumbled up together and they say find the derivative, they mean it's implied that you should use implicit differentiation. So derivative of x squared, 2x. Derivative of some stuff cubed, 3 times my stuff squared times the derivative of my stuff. Derivative of tangent of some stuff is going to be secant squared of that stuff times the derivative of the inside stuff. Okay, so the derivative of x times y, I have to use the product rule. So derivative of x is 1 times y plus x times the derivative of y. You can either think of the derivative of y as just y prime, or if you prefer, you can say, oh, it's 1 times the derivative of the inside, which is y prime. I would prefer to do it the first way. Plus 0, derivative of 5. Here's the extra additional little bit of terribleness this problem has. There's a y prime here and here, but this y prime is kind of stuck with this 1 times y here. And the only way I can really kind of get this piece apart from that piece is to distribute the secant square here. So that's what I'm going to have to do. I'm going to have to distribute secant squared of xy to each of these things that's multiplied by before I can then collect my y primes on one side. So I have 2x plus 3y squared y prime equal to secant squared of xy times y. I would probably write the y first. It's usually pretty standard to write things you're not taking the trig function of in front of the trig function. And then plus x times y prime times secant squared of xy. And now we can identify the things that have y primes and the things that don't. To bring them all to the same side, again, doesn't really matter which side you pick. I'll bring my y primes to the right this time just to change it up. So I have 2x minus y times secant squared of xy. And I'm going to do the thing here where when I bring this over here, I'm also going to factor out a y prime. I'm going to factor out a y prime. I'm left with an x times secant squared of xy. When I bring this over, it would have been minus 3y squared y prime, but I'm factoring out the y prime, so it's just minus 3y squared. I think it's a perfectly reasonable step to save yourself, so you don't have to, because these problems are always like a lot of writing. You're like writing on the same thing like 3 or 4 or 5 times. If you can save yourself a step, I encourage you to do it. So then dividing by that, we get 2x minus y times secant squared of xy divided by x times secant squared of xy minus 3y squared equal to y prime. Yeah, it's terrible. Okay. I have 2 more things to say about this. Let me just grab one example though. Sorry, there's one. No, come on. Got my phone sometimes. Apparently not. Oh, there we go. Okay. Let's see. Yeah. The reason I'm looking for an example is because coming up with the next kind of example can be challenging to do. Oh, nope. All right. Well, I guess not. Okay. So let's do the following. Yeah. Let's say we have y to the 4th plus, sure, x minus 2y cubed equal to, sure. Sorry, my brain is let's see, 1 plus 0 equal to, sure, x cubed. Yeah, I like cubed minus 7. Cool. And we want to find dy dx. That's a bad way of phrasing this. Sorry. Let me write this instead. Find the equation of the line tangent to the above curve at the point 2, 1. Yeah. Cool. So in calculus, has to find the equation of a line. We already have the point. What do we still need? We need the, starts with an S. We need the slope. And to find the slope, we need to take the derivative. But here's what I want you to see. We're going to take the derivative, and we're not going to solve for y prime. Let me show you what I mean. So taking the derivative, we differentiate both sides. That's our first step always. I'm going to get 4y cubed times y prime, or dy dx if you like, either way, plus derivative of some stuff cubed is 3 times my stuff squared times the derivative of the inside. Derivative of x is 1. Derivative of 2y is 2y prime, equal to the derivative of x cubed, which is 3x squared. Derivative of 7 is 0. Normally, if they said just to find the derivative, we would then do all the algebra we've been doing to solve for y prime. But here they didn't say that. They didn't say find y prime or find the derivative in general. They said find the slope of the tangent line at this one point. So plug in that point to find the slope. So we're going to plug in right now x equals 2 and y equals 1. So watch. We're going to get 4 times 1 cubed times y prime plus 3 times 2 minus 2 times 1 squared. I really don't even need to write anything else because that's 0. Equal to 3 times 2 squared. When people do this or ask problems like this, a lot of the times, a lot of things will become 0. So look out for the zeros, right? You shouldn't have written, once you saw that this was 2 minus 2, you should just be like, oh, 0. No need to write any more down there. So what they really have is 4 times 1 times y prime equal to 3 times 4. Or y prime is equal to 3. There's my slope. And then my equation is going to be y minus the y value equal to the slope times x minus the x value. Or solving for y equals 3x minus 6 plus 1 is minus 5. So when you're asked to find the slope of the tangent line or the equation of the tangent line, and your function is defined implicitly, do the usual first step, differentiate both sides, but then immediately it's almost always to your advantage to plug in the point right away and then find y prime. You're not plugging in for y prime, right? My y prime still just gets to stay as y prime, but I'm plugging in for every other x and y, the appropriate x and y value. What time? Okay, one other thing, yeah, cool. So one other thing I'll say is sometimes you're given something that looks really, really ridiculous. Sure. Something like, for example, y to the fourth plus x squared equal to, sure, x cubed plus y over tangent of x. Tangent of x plus 1. And although I certainly could, I really don't want to have to use the quotient rule right off the jump here, because not only, so the right side is going to be terrible when I do the quotient rule, but then I'm still going to have to then do the algebra of solving for y prime, which is really, really awful. So if someone happens to give you something implicit like this, you have choices, you have options. You can manipulate this equation algebraically before you take the derivative of both sides. Normally I wouldn't, except in the case where I have fractions. So I can say, oh, I really have, now it's still going to be kind of terrible because I made something that was terrible. Y to the fourth plus x squared times tangent of x plus 1 equal to x cubed plus y. And no, I don't really want to. I'm just going to take the, yeah, I made this really extra awful here. I would probably multiply it out, I guess, even though that seems terrible. So y to the fourth times tangent of x plus y to the fourth times 1 plus x squared times tangent of x plus x squared times 1. Okay, it's kind of a gross problem. We can still handle it. So now we're going to differentiate both sides, and we're not going to have to use the quotient rule at all, which is definitely a bonus. It's still going to be pretty gross because I made it pretty gross, but let's do it anyway. So here we're going to use the product rule. We're going to get 4y cubed times y prime times tangent of x plus y to the fourth times the derivative of tangent, which is secant squared of x, plus, now we're over here, the derivative of y to the fourth is also 4y cubed times y prime. Here we're using the product rule. Derivative of x squared is 2x times tangent plus x squared times the derivative of the tangent, which is secant squared of x, plus the derivative of x squared, which is 2x, equal to the derivative of x cubed, which is 3x squared, plus the derivative of y, which is y prime. Okay, I mean, this is kind of gross, but sure. There's all my y primes. So here's why multiplying this out was a good choice, I think. If I had just done this first thing as the product rule like that, then I would have had a lot of figuring out, multiplying out to do afterwards to isolate my y primes from my not y primes. But here, since I multiplied out first, all my y prime things are kind of already on their own. So let's bring the y primes to the right. So on the left-hand side, I'm going to have y to the fourth times secant squared of x plus 2x times tangent of x plus x squared times secant squared of x plus 2x, and then I'll bring this 3x squared over as well. So minus 3x squared equal to, I'm going to have y prime times 1 minus that minus 4y cubed minus 4y cubed tangent x. Right, I already factored out the y prime from each of those. And then finally, I don't really want to write it, but I will. Y prime equals all of this divided by that. This problem is an extreme example, I feel like. So y prime is y to the fourth plus secant squared times secant squared of x plus 2x times tangent of x plus x squared times secant squared of x plus 2x minus 3x squared divided by 1 minus 4y cubed minus 4y cubed tangent of x. So again, the takeaway here is that with implicit differentiation, we are always treating y like a function of x. When you take the derivative of some function of y, you do the derivative, but then you have to multiply by the derivative of the stuff, which is y prime. And that's always going to be the case for this implicit differentiation stuff. So really, implicit differentiation is just the chain rule again.